All right, section 8.3, superposition and interference of waves. Okay, so superposition of pulses and interference. Okay, so this is kind of when two waves pass through each other, okay, or in superposition is when they pass along the same way as each other. But so when two waves pass through each other, they interfere with each other. So two people talking, okay, makes it hard to hear. Okay, because when they occupy the same space at the same time, they are superimposed. So what happens, okay, we have pulse A going one way, whoops, pulse A going one way, pulse B going another way. Okay, what happens is, okay, the region where they overlap, okay, pulse A wants to be down here, pulse B wants to be here, and so they actually like combine together to get this weird kind of overlap or superimpose with each other. So the principle of superposition is the displacement of the combined pulse at each point of interference is the algebraic sum of the displacement of the individual pulses. Okay, so if we have pulse A and pulse B, okay, the resultant pulse is we just add the two up, like their displacement. So this is going to be twice as high. Constructive interference is when the overlap of the pulses creates a pulse of a greater amplitude. So in this case here, we have these two that are superimposed, and so our interference actually ends up being a lot bigger. So we get this greater amplitude. Destructive interference is when we have a pulse that's down below, okay, and then pulse B is above. Okay, our resultant pulse is kind of in between here. Okay, and so the overlap of the pulses creates a pulse of lesser amplitude. So that's destructive interference. It actually reduces the size of the pulse. Okay, so constructive interference kind of just showing. So we have pulse 1 here moving this way, pulse 2 moving that way, or A and B, I guess. Okay, so that's amplitude is 1 and 2. When they superimpose, we get an amplitude of 3, and then they continue along their way, A being 2, B being 1. Okay, destructive interference. So if B is down below, but 1 amplitude, A is 2 above. Okay, when they superimpose, our resultant is just going to be 1 above. And then again, they continue along their way, okay, and have the same amplitude as they did before. Okay, so total destructive interference occurs when two pulses completely cancel each other out. So in this case, both like pulse A and pulse B have the same amplitude, equal and opposite. So when they actually hit, like as they meet in the middle here, each one cancels each other out. And then as it goes on, it'll continue, like A will be above, B will be below. Okay. So the inversion of a reflected pulse in a fixed spring. Okay, so this one, the spring's fixed against this wall. Okay, so the actual spring position, okay, and then like these green dots are the original incident pulse, and then the blue dots would be the reflected segment of the pulse. So as the spring goes in and hits this fixed point, okay, we get some, like as it wants to start coming back, the reflected segment, the pulse would be down here. Okay, the original incident pulse is up here, so that it's going to kind of find that middle point. So we get some destructive interference in that case. Okay, and then as it evens out, we have full destructive interference, okay, depending on what it is. So if the end of the spring is fixed, the reflected pulse must be inverted relative to incident pulse. So after it hits, okay, we got nothing for like, because the destructive interference, and then the reflective wave, it's going to be inverted compared to the incident wave because of the pulse. And then as it hits the next one, then we get some destructive interference. Standing waves and resonance. Okay, so just kind of showing, so we have our two different waves move in different directions. Okay, at point A, okay, we get where they overlap. So the actual position of medium at where the waves overlap is this point here. Okay, and so at some points we get constructive interference, at other points we get destructive interference. Okay, and then depending on what they look like, and so in this case, like if we have them going equal and opposite, this is full destructive interference at the bottom, this would be full constructive interference. So waves are in phase if two crests or two troughs overlap. This produces constructive interference. They're out of phase if the crest and trough overlap and produces destructive interference. Okay, standing waves in a fixed spring. Okay, so these are, again, half our wavelengths. Okay, antinodes oscillate between shown positions. Okay, and then the nodes, so the antinodes would be in between, and then the nodes, whoops, moving the head here. Okay, the nodes are where they overlap. Okay. So in music, we talk about like there's different wavelengths for hearing and stuff. Okay, and so like the first harmonic, okay, has these larger nodes. Okay, second harmonic, okay, the wavelength basically is cut in half. Okay, and so on, and so and like the fifth harmonic, we're gonna have 5 antinodes. Okay, and that's where like where we get those. So there must be a node at each fixed end with an integral number of antinodes in between. Okay, resonating air columns. Okay, you can read about this. It's in your textbook. So reflection occurs at the closed end. Okay, and then we get the sound as it comes out. And so a longer tube like this, they're actually going to cancel each other out at the top. So air is free to oscillate in the end at the open end, which is our antinode. Okay, closed pipe resonance, okay, occurs when an antinode occurs at the open end, resulting in a louder tone. Okay. Okay, the fundamental frequency is the lowest frequency to which an instrument will resonate. Usually we do a big project on all of this stuff. Okay, again, it's all in your textbook. You can kind of read over. But like when we're talking about like wind instruments and stuff, if you have a closed pipe, you got a quarter of the wavelength. Okay, where open pipe, you get half wavelength. Okay, an instrument with an open pipe or closed open pipe or open tube is open on both ends. The distance between the adjacent antinodes is 1/2 wavelength. Okay, and an interference pattern on 2 in-phase point sources. So this is where we have, in water, we have 2 drops here. You can see, so at points P1 and R1, so P1 is here, R1's here. Okay, those are constructive interference. Okay, and then at Q1, right here, you can see there's nothing really happening. There'll be the same over here. Okay, that's where we get our destructive interference, where the crest meets the trough. Okay, interference patterns generated by 2 in-phase points. So we can see, like, if these are the crests, where the crests meet the trough, okay, there's going to be coming out from here our interference patterns. And so you can kind of, again, read over these. So the central maxima is, so all points that lie on the central maxima are the same distance from each source. Waves from each source will arrive in phase. Okay, a nodal line or minimum marks the location where the waves are exactly out of phase. So those would be our nodal lines there. Okay, phase shifts equal to an odd number of the half wavelengths produce the minimum. And so on. Yeah, I'll try and find a video that'll kind of help you more. It's hard to describe this without showing it to you. So I'm just going through it, but okay, but phase shifts equal the whole wavelength, produce a maxima. Again, so a half would be the minimums, which we talked about. Again, and the further away they get from the central maximum is kind of the order of our minimum maximum. So our first, like our Q1 in this case, is our first order minimum. Okay, and then our R1 would be our first order maximum, and the next blue line would be our second order, and so on. Okay, and so yeah, if you want to read up on this a lot more, it'd be better. It's kind of hard to show in a PowerPoint video like this. Okay, and I'll try and find a better video on YouTube that kind of shows what I want.